Hello everyone. We're looking at section 10.5 today, which is going to take us to adding and subtracting radical expressions, along with some additional multiplying and dividing that we hadn't seen before. So basically we're looking at multiple terms is what the big change is. So we can add, subtract, multiply, and divide radical expressions with multiple terms. Examples of expressions with multiple radical terms could be something like 5 square roots of 7 plus 10 square roots of 7, or the square root of 2x times the square root of x plus the square root of y. So we can really pull back to what we know well, which is polynomials. So if I were to ask you, what's 3x plus 4x, everyone would say 7x. So translating that over to radicals and telling you nothing, what do you think if I was adding 3 square roots of 5 plus 4 square roots of 5? I end up with 7 square roots of 5. So just like we're counting up the number of x's over here on the left, you're counting up the number of square roots of 5. And that's sort of how you think of it. You're taking an inventory. Now we're going to use some vocabulary in this section, so I want to make sure that we go over some that we've learned already and then some we haven't pointed out so clearly. So when two radical expressions have the same indices and radicands, they are said to be like radicals. So let's look at this 2 cube roots of 10. 10 is called the radicand. That's that inside part. 3 is the index. Good. The cube root of 10, that whole unit, including the index, the radicand, and the root, is called the radical. So when they say like radicals, they're talking about that whole back portion. So what is 2? Well, just like in polynomials, he's a coefficient. He's the number part. So he's that coefficient telling you how many of a particular type of radical you have. So what do like radicals for 2 cube roots of 10 look like? Well, basically, you have to fix the cube root of 10 and you can change to any coefficient you want. That would create a like term on the outside as well. So 5 cube roots of 10 would work. You can have negative 2 cube roots of 10. You can have just negative cube root of 10. You could have 1/2 cube roots of 10. So what's repeating itself? The radical cube root of 10. And so that's what you need for like radicals. The index has to be the same and the radicand has to be same. And then of course there's infinitely many like radicals. So one of the things that I want to say is that in order to add or subtract, we need like radicals. So that's why we're spending some time defining this. So you have to have like radicals just like you have to have like terms to add and subtract. Okay, so let's get started here. Number 1, we have 9 square roots of 5 plus 12 square roots of 5. So how many square roots of 5 do we end up with? Well, you just add the 9 and the 12, and so we end up with 21 square roots of 5. Number 2, we have 2 square roots of 5 and another square root of 5, and then you have negative 4 square roots of 7 and the square root of 7. So see how I underline those a little bit different, because they're not all 4 like radicals. They have different radicands. So the square roots of 7s are like radicals, the square roots of 5 are like radicals. So in this case, we don't get down to a single term because we don't have all like radicals. So how many square roots of 5 do we have? Well, we have 3 of them. And how many square roots of 7? Well, we have negative 4 and then we add 1, so we end up with negative 3 square roots of 7. It doesn't matter what order you write those in as long as you take the sign with the term. So you could rewrite that as negative 3 square roots of 7 plus 3 square roots of 5. All right, what about number 3? Well, you can't combine those no matter what because they have different indices. This one is a square root. This one's a cube root. But that doesn't mean you can't simplify it at all. For instance, you can simplify the square root of 8. Remember, he has a hidden 4 inside. So you can break down the 8. That's 4 times 2. And then there's nothing I can do for the second term. There's no hidden cubes inside of 2. So the 4 comes out. There's already a 3 in front. So what do? You multiply. So the 4 comes out as a 2. I'll write a 2 here. And then they multiply. So you end up with 6 square roots of 2 minus 5 cube roots of 2. And again, you can't combine those any further because they don't have the same index. You're not taking the same radical. So when you plug in the cube root of 2, you don't get the same answer as if you plug in the square root of 2 into your calculator. All right, what about number 4? Take a look at it. Do we have a problem? Yeah. The indices match. You have cube root, but your radicands, your inside, do not match. And I can't simplify the square root of 17, so that's it. This is already simplified. So notice we don't have that nice rule we had for multiplication where you could just add under a radical. That doesn't work. And we talked a little bit about that in a couple sections ago back in 10.3 where the square root of 1 plus the square root of 2 is not the same as the square root of 1 plus 2. You can't combine the radicals that way. So your final answer is what you started with. So number 5, your radicands are different also. But this one I can simplify. I can simplify that square root of 8. So let's do it. So for this guy, I have 3 times the square root of 4 times 2. I can pull out that 4 minus, I can't simplify the square root of 2 in that second term. 4 comes out as a 2. You already have a 3. We just talked about this. You get 6 square roots of 2 minus 5 square roots of 2. Oh, and look there. Now you have like radicals. So that happens a lot. So make sure you simplify the radicals before you decide if you can add or subtract. Because it may be that you have like radicals, you just can't see it because you haven't simplified them. So this actually ends up being 6 square roots of 2 minus 5 square roots of 2 is just 1 square root of 2, or square root of 2. And then let's look at number 6. Here we're taking the cube roots on both radicals, so they have a potential to at least be combined. I don't know that it'll work out that way, so let's simplify them individually and then just see what happens. So cube root, I can't break down the 2. X to the 6th is already a perfect cube because I can divide the index 3 into 6. But y to the 4th needs to be broken down as y cubed times y to the 1, and that's because we need a multiple of 3 as an exponent. But remember, you still have to add up to what you originally started with, which was the 4. All right, for the next one, next term, I have 7 cube root, and I can't break down the 2. I can't break down the y. 2 stays in. X to the 6 comes out as x squared because you divide by the index when you pull out. Y cubed comes out as y, and you're left with the cube root of 2y. And then this guy, we have 7 times the cube root of 2y. So it looks like these are like radicals. They have the same radical, cube root of 2y, cube root of 2y. Now, what's the problem? Your coefficients aren't like terms. So you can leave it like this. Another way that you'll see it written, or they can actually combine it to one single radical by just saying, well, this is x squared plus y, or sorry, x squared y plus 7, and then times, basically factoring out a cube root of 2y. And that's another way to see it, and you might see that on my math lab, so I wanted to show that to you. Like I said, on a test it doesn't matter to me, but this is just kind of showing that, hey, I've got a like radical. Let's pull that cube root of 2y out, and the front numbers, while we can't combine them, we just write them together in a set of parentheses, x squared y plus 7. Okay, so that is adding and subtracting. Now let's look at multiplying. So with multiplying, again, we're going to push over to radicals to polynomials because that's what we're most familiar with. So radical expressions often contain factors that have more than one term. Multiplying such expressions is similar. My words are just not finding me today. Of finding products of polynomials, i.e. distribution or foiling. Some products will yield like radical terms, and then we will be able to combine them based on the approach we had on the first page. So if I tell you nothing on number 1, what would you think to do here? Distribute. Good. And that's exactly what we're going to do. So what's the square root of 2 times the square root of 6? Well, the 6 is on the outside of a radical. The 2 is on the inside, so we just end up with 6 square roots of 2. Plus the square root of 2 times the square root of 10, you just end up with the square root of 20. So remember this rule. If you have the nth root of a times the nth root of b, that's the same as the nth root of ab, but they both have to be under the radical with the same index. All right? You're not done because the square root of 20 has a perfect square in it, so we can simplify. I'm going to kind of factor over to the side here. I can factor 20 as 4 times 5, and I'll go ahead and pull that 4 out, and I end up with 6 square roots of 2 plus 2 square roots of 5. Now, hopefully you've done your other homework before watching this video so that you're more familiar with simplifying radicals now. All right, number 2. You've got 2 binomials. Square root of 3 minus square root of 5 times the square root of 2 plus 7. You FOIL. So we're going to FOIL, and actually I'll switch colors so these aren't running into each other. So we FOIL. So first, square root of 3 times the square root of 2 is the square root of 6. We have outer, square root of 3 times 7 is 7 square roots of 3. We have inner, negative square root of 5 times the square root of 2 is negative square root of 10. And then last, negative square root of 5 times 7 is negative 7 square roots of 5. Do you have any particular like radicals? And the answer is no. They all have different radicands. You can't simplify any of them. So that's it. Sometimes you get like radicals, sometimes you don't. And one thing that I'll tell you that you're probably not is look at all the different radicands in the original problem. All right, number 3. 3x minus the square root of 2 squared. So this is another FOIL problem. This is another FOIL problem. Don't make the rookie mistake. You cannot distribute exponents, and I'll write this here, cannot distribute exponents across addition or subtraction. So that means you have to rewrite this 2 times. So you get 3x minus the square root of 2 times 3x minus the square root of 2. Now here we're more likely to get like radicals because we have like radicals in our original product. So first gives me 9x squared. Outer gives me negative 3x times the square root of 2. Inner gives me negative 3x times the square root of 2. And last gives me positive, because I have 2 negatives. Square root of 2 times square root of 2 is 2. In this case, you do have like terms. Those are not opposite signs, so they don't cancel each other out. First term is 9x squared, so I'll copy that. I'm not erasing. Hold on, let me push my button. It's getting a little haywire. There we go. Negative 3x square roots of 2 minus another 3x square roots of 2 is minus 6x square roots of 2. And then plus 2. And that's it. You're done. All right, so we've done 3 problems of multiplying. I would say pause the video, try and do number 4 on your own, and then come back and see if your answer matches mine. I'm going to switch colors here. So square root of 5y plus 2 times the square root of 5y minus 2. So for those more comfortable with factoring, you can probably see that this looks like the format of a difference of 2 squares. So let's see what happens. We are going to FOIL this guy too. First, square root of 5y times the square root of 5y. We know that if we square a square root, then we end up with whatever's inside, so we just end up with 5y. Outer, we have negative 2 times the square root of 5y is negative 2 square roots of 5y. Inner, positive 2 times the square root of 5y is plus 2 square roots of 5y. And then last, negative 4. So inner and outer terms cancel, and we just end up with 5y minus 4. So 2 terms that are perfect squares if you're using radicals. All right, and our last guy that we're going to work with multiplying is number 5. So I'll switch colors here again, go to blue. cube root of y times the cube root of y squared plus the cube root of 2. So notice all the indices match. We have cube root on all of these. So what do? We distribute. So cube root of y times the cube root of y squared. Well, that's going to be the cube root of y cubed, because you're going to multiply y and y squared because they're both under the same radical. Plus the cube root of y times 2 is 2y. Now you're not done, because you can simplify the cube root of y cubed. Cube root of y cubed is just y, and then you have the cube root of 2y. And there you go. So little trick, make sure you look after you multiply to see if you can simplify any of those radicals, because you tend to make bigger radicands that you might be able to pull out some perfect powers. All right, let's look at page 3. So now we're looking at division with multiple terms, and we're going to look at rationalizing again. So quotients of 2 or more radical terms, in order to rationalize denominators or numerators that contain 2 terms, we use conjugates. So this may be a new word for you. The conjugate of the square root of a plus the square root of b is the square root of a minus the square root of b. So if you're looking at conjugates, let's say we have 3 plus the square root of 7. His conjugate, so this is the original. Looks like a D, not an A-L. Original. And then conjugate. You just fix the first term and change the sign on the second term. So the conjugate would be 3 minus the square root of 7. Or if you had the square root of 7 plus the square root of 5, then the conjugate would be the square root of 7 minus the square root of 5. So again, you just fix the first term, change the sign on the second term. That's what a conjugate is. Now, when you're trying to rationalize and you have more than one term, the old trick that I showed you back in 10.4, I think it was, doesn't work, because if you multiply top and bottom, let's say this is bad math, so don't write this down. If you do this, you're going to get yourself in a little pickle, because when you distribute, you just keep creating a square root on the bottom. It gets rid of the square root of 7, but then you attach it to the 2. And then if you did it again, it would get rid of the one attached to the 2 and create it where the 7 is. So that doesn't work. So what does work? Well, when you have 2 terms, you have to multiply by the conjugate. So what's the conjugate of 2 minus the square root of 7? It's 2 plus the square root of 7. And rule of algebra, if you multiply the bottom, you have to multiply the top. So now we're just going to do a lot of distributing and foiling. So on top, I'm going to distribute the 6, and I get 12 plus 6 square roots of 7. On bottom, I'm going to FOIL. So 2 times 2 is 4. Outer gives me 2 square roots of 7. Inner gives me negative 2 square roots of 7. And last, negative square root of 7 times square root of 7 just gives me negative 7. Simplify anything you can. So let's move over on top. Not much I can do right now. On bottom, the square roots of 7 cancel, and there you go. That's why we like conjugates. It always creates these inner and outer terms that cancel. A difference of 2 squares basically is what's happening. And so you just end up with 4 minus 7 on bottom, which is 12 plus 6 square roots of 7 over negative 3. Now you're not done yet, because we can reduce this fraction. So on top, you can factor out a 3. Now, you never factor out of the radical. It's always the coefficients. The other thing that I say is that you have what I call the perfect, actually I'll go red, the perfect triangle. All three numbers are divisible by negative 3. And you would want to divide by negative 3 because you don't really want to have negatives in the denominator. It's just bad math grammar. So we can reduce all of these by negative 3. So 12 divided by negative 3 is negative 4. 6 divided by negative 3 is negative 2. Just copy the square root of 7. And then on bottom, you would just get 1. Well, that just gives me negative 4 minus 2 square roots of 7. So that's what the final answer would look like in my math lab. Most likely they'll show you getting rid of that negative. Another way to think about this is you can pull out a -3 on top or a +3. You would cancel with a -1 and then just divide each coefficient by -1. Okay. Number 2. So we're still rationalizing the denominator, and we have square root of y plus 4 in the denominator. So I can't multiply top and bottom by the square root of y. That won't get me rid of the radical. So what do I multiply top and bottom by? The conjugate, square root of y minus 4. So square root of y minus 4 down here, square root of y minus 4. On top, you're going to distribute. So we get -8 square root of y. -8 times -4 is +32. On bottom, we're going to FOIL. Square root of y times the square root of y is y. Square root of y times -4 is -4 square roots of y. 4 times the square root of y is +4 square roots of y. And then 4 times -4 is -16. So inner and outer term cancel. Good, that was the radical. And we end up with -8 square roots of y plus 32 all over y minus 16. And I know you're really tempted. You see a 32, you see a 16, you see an 8, but can you reduce this fraction? And the answer is no. This is it. And that's because this y term right here, this guy, has nothing to cancel. He has nothing to give you. There's no coefficient that's a multiple of 8. So in this case, you can't factor out an 8 on the bottom and cancel with an 8 on the top. That's not going to work. So you're just stuck with what you got there. I know you want to do it, but don't. Okay. And number 3. So at this point, if we were face-to-face in a classroom, I would say give number 3 a try. Check with a partner, see if you got the same answer. So for you, I'm going to say pause the video and then come back and see if you get the same answer as me. So let me switch pen colors so you know I'm doing a different problem here. So notice they changed directions on us. We're going to rationalize the numerator. Also, notice that's the direction. You have to just sort of know what they want. And rationalize just means get rid of the radicals. You have to remember that. You're responsible to know what that direction means. Get rid of the radical is the fancy way to say that is rationalize. So there's more than one term. If it's just one term, like if we just had the square root of, ignored the 4 and just had square root of 3 on top, we would just multiply top and bottom by square root of 3. But once you had a second term, you have to use conjugates. So we're going to multiply top and bottom by the conjugate of the numerator, which is a square root of 3 minus 4, because we're rationalizing the numerator, not the denominator. So top and bottom, you have to multiply top and bottom by the same thing. And then notice here you just have lots of FOILing, so lots of practice of multiplication. On top, the square root of 3 times the square root of 3 is just 3. Square root of 3 times the negative square root of 4 is negative square root of 12. Square root of 4 times positive square root of 3 is positive square root of 12. And square root of 4 times negative square root of 4 is just negative 4 because the insides match. So you just get whatever's on the inside. Positive and a negative is a negative. On bottom, I have the square root of 2 times the square root of 3, which is the square root of 6. Outer gives me square root of 2 times negative square root of 4, which is negative square root of 8. Inner gives me negative square root of 3 times positive square root of 3. Those radicands match, so the square roots will cancel. You just end up with minus 3. And then last term on the bottom, negative square root of 3 times the negative square root of 4 is positive square root of 12. Okay, so go back, pause it, make sure that you understand all the math I just did there. Now we're going to start to simplify. On top, the square roots of 12s cancel, and I just have 3 minus 4 on top. I'll rewrite that. I'm just doing one step at a time. Come on, pen, right? There we go. And then on bottom, you've got some work to do. The square root of 6 is fine, but you can break down this 8 as 4 times 2. So the 4 comes out as a 2, so we get minus 2 root 2, then minus 3. 12 can also break down. He's 4 times 3, so this 4 comes out, just like the other 4 came out, and he comes out as a 2, so we get plus 2 square roots of 3. Almost done. On top I have negative 1. On bottom, we have no like radicals, so we just recopy all of that. And I always get questions, does the order matter? And the answer is absolutely not. This just happens to be FOIL order. You just have to make sure you get those 4 multiplications in. If you want to rewrite it with the larger radicand down to the smaller radicand, totally up to you. No real convention for this. So it's just your final answer. It's not pretty, but it's the right answer nonetheless. Okay, well that is it. That is adding, subtracting, multiplying, dividing radical expressions with multiple terms. Go give the homework a try, and we will move on to section 10.6. To be continued.